Hi everyone, my name is Radha, Assistant Professor of Physics at Institute of Aeronautical Engineering. In this session, I am going to talk about Introduction to Photonics, in which I am going to discuss about light sources, the basic light matter interactions in lasers, required components for lasing, characteristics of laser output, types of lasers, method for pulsed laser operation, spectral tunability, finally classes of lasers, laser safety and laser damage. Introduction. Photonics is the science of generating, detecting, and manipulating light. With the invention of the laser in 1960 by Weyman, photonics became an enabling technology for applications such as fiber optic communications, bioimaging, laser surgery, LED lighting, security, flexible electronics, wafer inspection and metrology, lithography for semiconductor device manufacturing, and many other uses that enable the lives we live today. The choice of light source for an application depends on the desired characteristics of the radiation. These attributes can include the power or intensity of the light, its spatial distribution, and how it will propagate. Whether the light is constant as a function of time or is emitted as a burst, and the spectrum of the light, which determines its specific color or range of colors. In this session, laser light sources are discussed initially, followed by light emitting diodes and lamp sources. In each category, details are given regarding the mechanisms of light generation, the unique characteristics of the output radiation, the wide variety of light sources available, and the particular applications that are targeted. Laser is a device that can produce a very highly directional, narrow intense beam of monochromatic coherent light. It was introduced by Weyman, an American physicist, is with building the world's first operating laser on May 6, 1960. He achieved this remarkable feat at Hughes Research Laboratories in California. Wyman's laser was based on theoretical work done by Charles H. Downs and Arthur Leonard. The laser he created emitted coherent light source. Lasers. Lasers are devices that produce light with properties very different than those of other light sources. For example, incandescent bulbs or LEDs. These unique characteristics enable a remarkable wide range of applications. Laser light can travel large distances as a narrow beam without diverging, allowing it to be used in laser pointers, laser light shows, and even for communication between satellites. The light can also be focused to a very tight spot, enabling subcellular microscopic imaging, reading or writing large amounts of data to from DVDs and Blu-ray discs, and photolithography, which is critical in the production of modern microelectronics. Furthermore, if this tightly focused light is confined to very short bursts or pulses, a high intensity lasers can be used for a variety of micromachining applications, including cutting, marking materials such as ceramics, glasses, and metals, as well as safe ablation of human tissues. Finally, laser light can have a very narrow spectrum or singular color that enables high resolution spectroscopy and optical fiber communication. It is a source of coherent light. It contains an optical oscillator that increases the amplitude of an optical field while maintaining its phase. This coherent amplification is achieved through light amplification by stimulated emission of radiation. The process of amplification is the result of stimulating an atom such that it emits an identical photon to one already present. This clone photon has the same phase, frequency, direction, and polarization as the original one. meaning they are incoherent. It is this coherent amplification of light that gives lasers their unique output characteristics. All lasers have three main components. Here you can see is the gain and the pump source. These gain and pump source will be arranged between the resonator. The main components of laser is gain, medium, pump source, and the resonator. The pump source is the mechanism by which a population inversion is produced in the gain medium. The gain medium is chosen to achieve efficient lasing action as well as the desired characteristics for the laser output. The figure shows the simplified diagram of laser including the gain medium, pump source, and optical resonators. Gain medium. It may be gas, solid, or liquid, which provides lasing transition. Pump source. Source of energy to create population inversion. Usually, this pump may be light source, flash lamp, another laser, can be electrical discharge or injection of current. Cavity. Need to circulate photons to stimulate emission on laser transition. Often mirrors around gain medium can be medium itself. These are the three main components of the laser. The resonator mirrors allow for selective reflection of incoherent photons produced by spontaneous emission back into the gain medium. Stimulated emission replicates these reflected photons and the sequential reflection or amplification process gives rise to a large number of coherent photons. Finally, a portion of these photons are transmitted through a partially reflecting mirror delivering the output laser beam. In the resonant cavity, we have two kinds of mirrors. One is 100% reflective, the other one is partially reflective. This partially reflective mirror will give the laser beam in the resonator. Light matter interaction in lasers. Light is generated from a laser as a result of following process. Electrons in a material move from an excited energy level to a lower lying energy level and produce photons that contribute to the laser beam. The fundamental interactions between light and matter are the basis for the analysis of laser operation and properties of light. The interaction between atoms or molecules in a laser material and the photons that makes up the resulting laser light. The figure shows the evolution of energy level diagram for increasing interactions between atoms from left to right. This shows the for single atom, this is for molecule, this is for insulating materials, this is for semiconductor material. After making bands, this gap shows the differentiate. This gap can define the material properties. Atomic energy levels are determined by the interactions of electrons with the atomic nucleus and other electrons. As electrons move or make transition from one energy level to another, specific amount of energy are either absorbed or emitted. This is the main mechanism by which photons of light can interact with atoms of matter. These energy levels and their associated photon energies are uniquely dependent on the electronic structure of the atom. Molecules are made up of two or more atoms and their energy levels are dictated by interatomic forces. In addition to electronic transitions, molecules also possess transitions associated with vibrational and rotational interactions, which lead to a more complex set of energy levels compared to simple atoms. If we have one atom, the energy levels are discrete. If we have more atoms, there is an influence on the energy levels interaction between these atoms. The splitting of energy levels takes place because electrostatic field from one atom get perturbed from the second atom. For a large group of identical atoms or molecules where the constituents are isolated from one another, such as in a dilute gas, each atom or molecule has the same set of discrete energy levels. However, when atoms or molecules are brought close together, such as in liquids or solids, a variety of intermolecular interactions became increasingly important, and the initially discrete energy levels associated with the isolated atoms or molecules gradually broadened into a collection of numerous densely packed energy levels. See here. Densely spaced energy levels that form energy bands. Based on these bands, material properties can be defined. These valency and conduction bands and their spacing gaps are illustrated in the figure for an insulator and for semiconductor. Here you can see for the insulator there is a huge gap between these valency band and the conduction band. In the case of semiconductor, this gap is less than 3 electron volts. Radiation processes. Regardless of the type of matter that makes up a material, there are three fundamental processes by which light interacts with atoms, creating upward and downward transitions between energy levels. Spontaneous emission, which occurs when an atom is in an upper energy level or excited state and decays spontaneously to a lower energy level, even radiating a photon of light when it does so. Which means initially the atom is in the higher energy level. Spontaneously, it coming down, it emits the photon. We call it as a spontaneous emission. Since each material has a unique set of energy levels, the emitted photons possess energies that are specific to that material. These photon energies are related to the frequency nu and wavelength lambda of the light, while delta E equal to difference of energy between the energy levels, which is equal to h nu that equal to hc by lambda, where h is the Planck constant and c is the speed of light. Here you can see the three processes when the radiation interacts with the matter. The first one is the spontaneous emission. In this case, already atom is in the excited state. When it coming down, it emits the energy which is equal to difference of these two energy levels. Here you can see emission of the photon. In the case of absorption, the atom is in the ground state. Upon instant of the radiation, this atom gets make the transition from ground level to the excited state. This we called as the absorption. In the case of stimulated emission, in this case is also the atom is in the excited state. Upon instant of the another photon, this excited atom gets stimulated to make this transition to the ground level. In this case, two photons are emitted which are identical in wavelength, frequency, and the energy of the instant photon. The second process shown in the figure is absorption. Absorption occurs when the atom is initially in the lower energy level and a photon with energy h nu is absorbed by the atom, raising it to the upper energy level. The final process in the figure is the stimulated emission. Emission is essentially the inverse process of absorption since it also requires a photon of energy h nu to be present, but the atom is initially in the upper energy level. The photon stimulates the atom to radiate a duplicate photon having the same characteristics as the original one, including energy, direction, phase, and polarization. Stimulated emission produces photons at the expense of energy stored in atom, which gives rise to amplification of the light or optical gain. This phenomenon is central to the operation of a laser. Transition cross-section. One term useful in quantitatively characterizing this atom radiation interaction is the transition cross-section. It is represented by sigma nu. This value describes the strength or probability that the interaction will occur and is applicable to all three of the radiation processes discussed above. The transition cross section is depend on the frequency or wavelength of the photon of interest. It is centered on the resonance frequency mu naught, where sigma nu is largest and drops as nu deviates from the mu naught. Here you can see at mu naught the transition cross section is maximum. When it deviates from mu naught, this cross section is going to decrease. This figure shows the line shift function G. A few A few key quantities of interest are the peak transition cross section sigma naught, which is equal to sigma of mu naught, the line width delta nu representing the full width at half maximum. Here, which is full width at half maximum, and the area S, which is called the transition strength or oscillator strength. A common way to write transition cross section is in terms of its strength and profile, which is equal to sigma nu S of G nu. Here S is the area, which is called the transition strength or oscillator strength, where the line shape function G nu is a normalized function with unit area. This allows one to separate the strength of a transition from its frequency dependence. A number of processes contribute to the delta nu associated with G nu, including homogeneous and inhomogeneous broadening. Since equation applies to stimulated emission, its importance in the laser amplification bar gain processes should be clear. A large transition strength can give rise to a large gain coefficient for lasing, while the line shape helps determine the frequency response and gain bandwidth. Population inversion. The depiction of the radiation process you can see here illustrate that the impact is tied to the population of the atoms in the various energy levels. For a system in thermal equilibrium, the probability that an atom is in a particular energy level is given by the Boltzmann distribution, which is equal to n2 by n1, which is equal to exponential of delta E by kt. This one is the equilibrium distribution. Here you can see population inversion, which means number of atoms in the ground state, that is n1, is less than number of atoms in the excited state. Once we achieve the condition, we can get the lasing action. Here you can see probability of occupation of the atoms at particular energy levels, which is going to decrease exponentially by increasing the energy levels. This probability exponentially decreases with increasing energy levels. If one considers just two energy levels, E2 and E1, you can see in the figure, then the Boltzmann distribution gives the ratio of their respective populations, that is N2 and N1, which is equal to exponential of minus delta E by kt. Here K is the Boltzmann constant, T is the temperature. Typically, energy level difference, that is difference between the two energy levels, delta E, for a laser transition are two orders of magnitude larger than kt at room temperature. And so N2 is very less than, N2 by N1 is very less than 1. Since most of the population is in the lowest energy level, the process of absorption dominates here, which is typically how light interacts with most of the matter that we see in our home, like LEDs, lamps, and sunlight as well. Furthermore, with little population in the upper energy level, stimulated emission is highly unlikely. However, if significant population could be transferred to higher energy levels such that N2 exceeds N1, a non-equilibrium condition known as a population inversion. In this case, number of atoms in the excited state, which is greater than number of atoms in the lower level, that is ground state, is known as the population inversion. Population inversion is a prerequisite for lasing action, since stimulated emission is the means by which amplification is achieved. As per discussions, critical components of a laser are a gain medium, a pump source, and a resonator. As we discussed before, gain medium, pump source, and resonator. The details regarding the function and operation of these components are the component. The first one is the gain medium. Its function is acts as a medium for population inversion and determines laser emission properties. Example for this gain medium is atomic or molecular gases such as neon and argon and carbon dioxide. Ions in crystals or glasses. Ions means lanthanide ions, for example, neodymium, yttrium, terbium, and transition metals like chromium. And semiconductors such as gallium arsenide, indium gallium arsenide phosphide. Pump sources serves as a energy source for inverting population. It may be electrical discharge, flash lamp or arc lamp, other laser electric current. Resonator. It provides feedback mechanism for amplification and selects spectral and spatial properties of the lights. For example for this, bulk mirrors in solid state lasers, cleaved or coated facets in lasers, diode lasers, Barak reflectors in fiber lasers. These are the three components and its functions. Gain medium. Gain in a laser medium can be described by considering two energy levels with population densities N2 and N, and is an associated transition cross section sigma to 1 as described by the equation I equal to I naught e power I equal to I naught e power sigma 1 2 of n2 minus n1 times n. Since population exists in both levels, absorption and stimulated emission will occur within the medium. If I naught is the intensity of a beam before entering a material that has a length of L, the light intensity I exciting the material is given by I equal to I naught e power sigma of 1 2 of n2 minus n1 times L. If n1 is greater than n2, absorption is the dominant process and the exponent in equation is negative. If if n2 is less than n1, this equation exponential is negative, resulting in attenuation of the beam. In this case, the product of the population difference, that is delta n, and the cross section is known as the absorption coefficient and is a measure of the loss in the intensity per unit length. If absorption dominates, which means N2 is less than N1. Conversely, if N2 exceeds N1, a population inversion exists and stimulated emission will dominate over absorption. Equation then possesses a positive exponent giving rise to amplification. The product sigma times delta n is then defined as the gain coefficient G, representing the gain per unit length. In order to maximize the amplification, a laser gain medium should possess a large transition cross section at the wavelength of interest and be able to support a significant population inversion. In practice, more than two energy levels necessary to achieve a population inversion because a two-level scheme allows at best only equal populations of the upper and lower levels, thereby leading to no amplification. Here you can see energy level diagram for 3 and 4 level lasers, which is adapted from reference 10. To overcome this problem, Alternatively, 3 and 4 level laser systems essentially decouple upper and lower levels. A 3 level system pumps population from ground state to the excited state, which rapidly decay to the level from which stimulated emission occurs. Level 2 is often referred to as the metastable level since it has a long lifetime. The lower level, where the simulated emission terminates, should be depumped rapidly to dispose of its population. These two requirements, that is long lifetime for upper level and short lifetime for lower level, help guarantee that a reasonably large population immersion can be maintained. Since level 1 is also the ground state, it possesses an inherently large population, therefore, substantial pumping must be implemented to ensure that more than half of the atoms reach the metastable state. These disadvantages of a 3 level system are avoided in a 4 level system. Here, level 1 is situated just above the ground level is 0. Typically, rapid non-radiative decay depopulates this level, which means atoms in the level 1 non-radiatively decay to the ground level, making a population inversion easier to achieve. Population densities also change dynamically depending on a variety of processes, including radiative and non-radiative decay pathways, pumping rates, as well as absorption and stimulated emission rates. Depictions of practical 3 level and 4 level laser systems along with their decay pathways are shown in figure. Here you can see when radiation interacts with the matter of ground state, these atoms are making transition to the higher energy level and non-radiatively decay to the lower level L2, which we called as the metastable state. Then it makes the transition to ground state to emit the photon of laser beam. In the 4 level system, when the radiation interacts with the ground level atoms, these atoms make the transition to higher energy level and make the non-radiative decay to level 2 and radiatively decay to level 1 and non-radiatively decay to ground state. The analysis of population dynamics for such multi-level systems can be complicated. Pump source. A variety of different pumping mechanisms are used to achieve population inversions, and these are typically dictated by the gain medium. In all cases, the goal is to achieve pumping rates, that is, atoms per unit time per unit volume being raised to a metastable level sufficient for establishing sustainable stimulated emission. For gas lasers, the pump mechanism is typically via electric discharge, where an electrical current is generated in a low pressure gas. The electrons transfer their energy to atoms via collisions and promote these atoms to higher energy levels. In semiconductor lasers, electrical pumping gives rise to charge carriers within a junction that provides the upper laser level population. Optical pumping is the most common mechanism for generating population immersion in solid state lasers, and, and this is enabled using either a lamp or a separate laser. Flash lamps or arc lamps produce intense light emission and typically have a broad emission spectrum of wavelengths that can be matched to the absorption bands of the laser medium. This figure shows the example for optically pumping a gain medium including flash lamp pumping and semiconductor laser diode pumping. Here you can see this semiconductor laser diode is used to pump the another measure. To efficiently pump the laser medium, the flash lamp geometry can take on different configurations, including a helix wrapped around a laser rod or laser rods inserted into an elliptically shaped or circularly shaped elongated laser cavity. Laser pumping is used when the pumping energy must be concentrated into a relatively small volume, delivered over a short period, or provided over a narrow bandwidth that gives the intense beam of radiation. Pumping via semiconductor laser has several advantages, including increased system efficiency, better light coupling into the laser medium, and compact geometry. Figure shows a typical end pumping end pumping configuration for a semiconductor laser diode. However, other geometries such as side pumping and close coupling configuration are also exist. When a laser diode pumps a solid state gain medium, it is it is referred to as a diode pumped solid state laser system (DPSS). DPSS lasers can be used to generate very large pumping rates for other solid state lasers. Resonator. In a laser, the gain medium is placed inside an optical resonator that provides feedbacks. This feedback mechanism allows for photons generated by stimulated emission to be reflected back into the laser medium for further amplification. A common example of a laser resonator or cavity uses two mirrors separated by a specific distance d. Here you can see these two mirrors are separated by distance d. Between these two mirrors, the photons are reflected back and forth to get more amplified beam is coming out of the partially coated reflector. Typically, one mirror is highly reflective at the laser wavelength while the other mirror is partially transmissive so that a portion of the light exits the cavity as the laser beam. One benefit of this feedback mechanism can be gleaned from equation I equal to I naught e power sigma of 1 2 of n2 minus n1 times n, which gives the optical gain in a laser as the product of the gain coefficient and the laser medium is here. For a given laser, for a given laser gain medium extending L could be a means to generate sufficient gain for lasing, but there are clearly partial limitations to simply elongating the gain medium and increasing the effective optical path length can provide a means for enhancing gain. This can be achieved by placing laser medium, which means gain medium, inside an optical resonator. This is illustrated in figure when comparing upper two graphics in figure which show gain medium with and without resonator. Here you can see the resonator, here there is no resonator. Depiction of single pass through an amplifier on the top and multiple passes through an amplifier when a resonator is present. The dotted portions illustrate the effective increase in the optical path length provided by the resonator. Common resonator configurations are represented in the bottom. Here you can see nearly planar complex resonator. Here is the planar resonator. Here is a nearly planar concave resonator. While the additional passes allow for increased gain when compared to a single pass geometry, after just a few passes through the gain medium, the light begins to leak outside the cavity. For this optical feedback to work efficiently, the resonator must be designed to be stable such that light stays inside the cavity and do not leak out. The parallelism of the mirrors as well as their curvatures play a large role in the design of stable laser resonators. The lower part of the figure shows a few typical resonator configurations in addition to the resonator induced feedback leading to increased gain. It also decreases the beam divergence significantly. This decreased beam divergence is responsible for the high degree of collimator pressure. Since an amplifier with positive feedback is an oscillator, a laser is often called as an optical oscillator. For laser oscillation or lasing to occur, two conditions must be satisfied that are bound by the gain medium and the resonator. The first condition dictates that optical gain, that is G, will be greater than the total loss, that is alpha hour, for a single round trip through the cavity. Parasitic losses within a laser cavity typically come from absorption within the gain medium itself, optical scattering, or absorption from any element within the cavity. So, optical gain should be greater than the loss by the absorption. Necessary losses, such as those associated with transmission through the output coupler, must also be considered. The second condition requires that light waves within the resonator must be coherent, coherently add or constructively interfere with one another. Only light that possesses an integral number of oscillating waves that fit within the cavity length G will be supported. These standing waves are known as the resonator modes and are depicted in the figure. Here you can see resonator modes. Longitudinal modes differ from one another only in their oscillation frequency with the separation delta nu, which is given by C by 2D. Here D is the cavity length, C is the velocity of light. This frequency separation is typically small, that is about 0.5 GHz compared to the laser gain bandwidth, and any longitudinal mode that has sufficient gain can undergo lasing. There can be a single longitudinal mode or several hundred thousand modes depending on the gain bandwidth. On the other hand, transverse modes follow different transverse bands through the amplifier and therefore emits larger in size and in divergence. Depiction of, here you can see in the figure, depiction of longitudinal and cylindrical transverse modes produced by optical cavity. The frequency spacing of longitudinal mode in the lower left. The spatial patterns of the transverse mode are shown in the lower right. Here you can see the transverse modes. That is GEM modes. This is TEM00, TEM00, TEM01, 10, like that. Figure shows a variety of laser beam intensity distributions associated with different cylindrical transverse modes. These are defined by their transverse electromagnetic TEM distributions, the lowest order mode being TEM00, which has the more intensity compared to all others. Based on the discussion in this session, a laser can be considered a resonant optical amplifier whose output is fed back to the input with massive waves. These are the references that I used to make this session. Is this? Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.